So let us pick up from the last lecture. And the other day in the last lecture I was just telling you how we can understand that there could be an inverse square law if there is something which is coming out of this center, the point object, the point something coming out of this spherical surface, and there are no preferred directions, all directions are equally preferred. Then if we want to know what is the effect on the surface, naturally the effect of the surface for this value of r will change if the value of r is increased and the size of the sphere becomes larger. That's why I use the word kind of secular, this thing. Also, if there are things which are coming and concentrating over here from all sides, okay, and with equal preference, then also we can say that whatever culminates over here, that something I am calling, this will be proportional to the effect which is there. So effect is equal to something divided by the total area, surface area of the sphere, and that is, geometrically we know that area is 4 pi r square. There will be occasion to tell you how this 4 pi r square is obtained, but for now we'll say that the effect is proportional to 1 upon r square, and this wasn't the case. In the beginning there was no argument like that. There was no thought experiment like we have done here, and you have cooperated with us, wherein we find that in any case where there is a spherical surface, where there is a center, and in that case the effect which we obtain on the surface of the sphere, that turns out to be 1 upon r square. This is with the argument of a Gaussian argument, okay, in Gauss law, etc. So now if I come back to the universal gravitation system, the system comprises of two masses which are separated from each other by a distance r, and then because there is a law of attraction so that the two forces, they try to bring these masses close to each other. Now for the time being we will consider that these masses are kind of held in those places where I increase the value of m1 or decrease the value of m1 as you like, and so the variable m2 is also changed and the variable r is also changed. So this force, which I define as this is the value, just the value f of either of these two forces, F21 and F12. So then we find that in the law of universal gravitation, this F1 is proportional to M1 under the condition, under the constraint that M2 and R are not changed. F is proportional to M2 when M1 and R, the two other variables, they are taken as constant, they don't change. And F is proportional to 1 upon r square when the possible variables M1 and M2 are brought as constant. Now I can write for all these equations together, I can write that the force F, which results due to this defined system, this is proportional to M1 into M2 into 1 upon r square. And then now we have, if this is so, then what is known as mathematical consistency, which you may not be able to understand right now, but because of the mathematical consistency, I can say that because there is a proportionality, so there should be a constant of proportionality, and I can write this f is equal to some constant which we are writing as capital G over here, m1 m2 upon r square. So we obtained the formula, and I said in my first lecture that obtaining the formula is not physics, but once we have obtained the formula, then we try to analyze and synthesize as to what is the meaning of these things. So this G is the constant of the entire system, constant for the entire system. Now this capital G is called a universal constant, and why we call it along with other constants like h etc. as a universal constant, because it neither depends upon m1 nor on m2 nor on r, and also does not depend upon the force that is there. So this is independent of everything that is there, and I can say like now I'll just try to explain this and relate it to Coulombs law if the time permits. Now this you know, and I understand that you must be knowing that the force is, the unit of the force is Newton. So Newton is the unit here. Then I have the unit of, we'll try to find out as to what is the unit of G. M1 is kilogram, M2 is also kilogram in the MK system, and this is meter square. So that this gives the capital G, the unit of that is something, a number, Newton meter square. This is the unit that I am going to write, Newton meter square kilogram power minus 2. Then I don't emphasize, you can find out what is the value of G. Exact value in the MK system, in the meter kilogram second system, are what we call the SI units, but I'm not very this thing. So I have in the system that we have multiple variables, M1, M2 and R. These are all variables. So M1 will change, M2 may change, R may change, and so F will change. But capital G will remain a constant. So capital G, I can say that this constant capital G is not a function of the variables M1, M2 and R, also the resulting force F does not depend upon any of these things. So this capital G, the value that we obtain of the system that we have, we define that at the time of Newton, at the time of those who followed him, today, tomorrow and the day after are centuries hereafter, the value of G will remain the same. So this we call a universal gravitational constant. Universal gravitational constant. Universal gravitational constant. Now here is, with a little bit of change that we have, I'll just introduce to you what and then explain what are the things. The Coulombs law. In the Coulombs law, which is also an experimentally determined law, this is also an experimentally determined law. Cavendish, he established this law. Then we say, just replace this M1 for the time being by Q1 and this by Q2. The same R and the same equations like this. The only thing is that there is a possibility that the forces F12 and F21 may be opposite to each other and they are not attractive, they are rather repulsive forces, and then we write the same kind of equation. In both the cases this will turn out to be F12 and F21, and like this F12 plus F21 is equal to 0, this like this like this, this say, and of course what we do is that I will write here, say, the value of the charge. It will have occasion, the charge Q2, and this inverse square, which is like this. Okay, so here I'll write Q2, here I'll write Q1, and here I'll write Q1 and Q2. In that case, what happens is that I get a relation, which I'll write here in the red pen, that F with mathematical consistency is proportional to Q1 into Q2 into 1 upon R square. Okay, and therefore the F is equal to some constant Q1 Q2 upon R square. It's handy to write like this, and this constant in the system is 1 upon 4 pi epsilon naught, where epsilon naught is the permittivity of free space. We'll have occasion to deal with this elaborately later on, but because I was trying to introduce to you a multi-system, a multi-variable system, so I just took this as an example and hope that you know it from your high school classes, both these equations. This is the constant 1 upon 4 pi epsilon naught is equal to the constant of the system. Constant of the system. Now allow me to go back. Allow me to go back to this equation. F is equal to capital G M1 M2 upon R square. R similarly is 1 upon 4 pi epsilon naught M1 M2 Q1 Q2 upon R square, which will happen in the case of this. Okay, so the unit of G unit here, G unit, which turns out to be equal to some number into Newton meter square into kilogram square. Now let us try to understand this whole thing. So in the first instant I said that F is proportional to M1. So I'll write here that let there be M1 and let there be the force that we obtain. And then I have, graphically I can say that under the condition that this is, because this one is directly proportional to M1, so I have to get a line. Then this is the linear system, and I can say that here there is a condition M2 is equal to constant and R is also equal to constant. Of course we can do it with Q1 and Q2 and R. Now the constant of proportionality of this, with the help of this equation, what I am going to write is that F will be equal to F will be equal to capital G M2 upon R square. This I take as a constant because M2 is a constant, R is a constant. So this is this multiplied by M1. So I can say that this constant times M1. So the slope here, the slope which is the constant of the system, indicative of the constant of the system, delta F upon delta M1, this value will turn out to be equal to capital G M2 upon R square, where all these things are constants, multiplied by M1, so this becomes the slope of the system. Similarly, if I plot F versus M2, F here in newtons and M2, I'll get a similar thing which is easy to understand. And what I have here, F as a function of M2, and I will get M1 and R as constant. Then the slope that I will get here, which is indicative of the slope, will be equal to of the constant. So slope will be equal to capital G M1 upon R square. Okay. In the third instance, and for this, if I plot and I will take the liberty to in the third instance, when I have F on this side and 1 upon R square in meter minus 2 per meter, and this is F. So what do you expect here? Often my students say that this is inverse proportionality, but no, here I have taken a direct proportionality. So F is proportional to 1 upon R square under the condition that M1 and M2 are constant. So this will be what I will obtain is a graph again like this, and the slope of the system for this graph, slope is equal to capital G M1 M2 because when I write that F is proportional to 1 upon r square. Then I say that this is equal to capital G m1 m2, this as the constant for the thing, and 1 upon r square. Since it is difficult to understand a unit like meter raised to the power of -2 or per meter, okay, so to appreciate that, therefore I again make a plot that this is F and this is R. But as you can see that as the value of R is increased, so the value of F will keep on falling. So this will be a curve like this. This is a nonlinear curve, as I told you, which asymptotically goes to 0 here, and because F is here a constant times K into R raised to the power of -2, and therefore the slope will be df dr, because R is the variable and this variable is in meters, so this will be equal to K into, with the formula that we had for the differentiation, -2 R raised to the power R power -2 minus 1, which is equal to -2K R power -3. So you can see it is evident, it is just before our eyes that the value of the slope keeps on decreasing until it finally vanishes symptotically as the value of R is increased. So these are three things I give it to you, and I want you to think about these things, because I told you that the physics starts here. Physics does not stop here. Okay? So there is a linear relationship between between F and M1, F and M2, and F and 1 upon R square. The relationship is linear. But when I make this as a function of R, then we see that this is kind of a nonlinear function where the value of the slope is -2 into K into R raised to the power of -3, which vanishes very fast. Okay, so this is it for today, and in the next lecture I'll discuss more about it, and I give you time to ponder over. To ponder means आप गौर कीजिए, आप खोज कीजिए, आप सोचिए, आप समझिए, आप सवाल पैदा कीजिए, क्योंकि अगर आपकी तरफ से सवाल नहीं आएगा तो आप और जवाब अपने आप से मांगिए, अपनी किताब में देखिए। हमारे कुछ गुरु लोग क्या करते हैं कि इसको यहाँ पे कहते हैं कि F is proportional to the product of the masses and is inversely proportional to E square R. No. It is proportional to M1, proportional to M2, and proportional to 1 upon R square, or proportional to R raised to the power of -2. And it has a very deep meaning. Not like that we give the formula, you frame a question, you put it there and you try to answer the question. So instead, I require you to go through this lecture at least 2 times and give a double that time with your books with you, and try to understand what I am trying to, what I have tried to give to you, which is very valuable. and it opens our minds to obtain the physics and the meaning of the physics behind any kind of expressions. This time we have just taken three variables, m1, m2 and r. Also, yani, just like q1, q2 and r in the system of Coulombs law. And these two equations that are there, they are experimentally determined once, and the values have been fixed for G and also for epsilon naught. So long, I hope you enjoyed.